actually, I'm hoping that this talk will be like 2 hours really, but hopefully the second part actually might touch on what the previous speaker, Ismo, I think his name was, what he was talking about. And anyway, we'll see. So just a quick note, a few things, QP, quantum potential, Stern-Gerlach. I just wanted to, because I used some initials, I just wanted to make sure you were all aware of what they mean. So we initially, when we built this equipment, and Vincenzo actually got his PhD for constructing this and carrying this work out. And I'd like to impress on you that we did actually start from literally an empty room, so to speak. So we firstly looked at 3 gases. So this shows where this is helium gas that's being pumped in to the system, and how we actually use it to form pulses of helium. Now, let's move on from that. Now, this is the equipment. The bit of a technology you just looked at is on the far left-hand side of this picture. You can just see there's a black pipe and that there, and you can see that's where the gas is coming in. Anyway, it goes through all sorts of various stages, which we'll talk about, and then eventually ends up down the far end where there's the detector. So this is the Stern-Gerlach magnet here, top left-hand corner, and there's a schematic of the magnetic field. This is the 3 gases that we used, neon, argon, and helium. And then, as you can see, this was partly to just explore that we could do this and actually produce the atoms in an excited state, which we can detect, but also to, it's sort of test out that actually what we were doing was correct. But we selected helium, and the first thing was about weak measurement. Now, weak measurement, just to remind you, what you have to do is you have a beam of particles, as you see, coming in from the left on this schematic, and it approaches. There's 2 magnets involved, one weak, one strong, and initially you have to set the spin, or the spin axis, at a particular angle, which is represented there by theta and the red arrow. I won't go through the mathematics because we've only got half an hour, but I'll whiz on. All right, it goes through the weak stage, which in this case was what we call a 2-wire magnet. In other words, it's just literally 2 wires carrying quite a heavy voltage, which took some design work. And then eventually you can see that from the big red arrow there, that is the direction of the sort of magnetic field, and that's how you should see the spin axis. Right, and then you get the strong stage, which was that big magnet which I showed you previously. And then what you should observe is where you would see normally 3 dots, which I showed you on that detector picture. What you should see with this weak measurement, you should see actually one of those dots is shown on the right-hand side. You should see it to start to move. Right, as you increase the strength of that stage, you should see that moving up. And then, but eventually, of course, it will, if you can make the weak stage strong, then in fact, what actually happens is they all move, and you end up with 9 dots, believe it or not. But anyway, but the point is that there is in this intermediary stage where this kind of rather bizarre behaviour takes place, and this was the signature of something happening. And this is, see, the strong stage is set at right angles to the weak stage again. I see, and what this is really about is if you set your basis by, say, the weak stage, then what you're asking the question is what happens when I go over to, I transition to another basis, which is at right angles. That's the real question we're asking here. Now, normally, they're both strong, you go through one, it comes out, and then all those 3 beams go into the second one, and each of those beams is now set by the second stage, and that's why you end up with 9 different things. But the question is here, if you wind the weak stage up from 0, according to the theory, you start to see this rather odd behaviour, and that's what we were looking for. And in fact, there was lots of work done on this to actually get what theoretically should we see. Peter, who's at the meeting, actually did a certain amount of this, I think, if I remember correctly. Sorry, this was all pre-COVID, so it was a long time ago when we were doing a lot of this. I won't go through all these various parts here because I don't have time, but the end result was that, and Peter, I think, predicted this, that what you start to see, instead of seeing that relationship, that simple relationship, you actually don't even get that relationship. You start to get a very simple, a much more complicated, depending on the strength of the magnet. And so you see almost like it's almost looking like an interference pattern. It's not, but that's what it looks like. And in fact, Vincenzo obviously ran the experiment, and as you can see, I think it's fairly convincing that we were seeing something approximate to what Peter predicted, what Peter's predictions were. There is a problem with this, is that the scale of the bottom axis, we obviously had a scaling problem, and what we were hoping to do was actually, get to grips with that scaling problem and work it out. And what we were trying to do, and this goes back to when we talk about quantum mechanics in its barest form, is that when you try to build an experiment, you have to remember that you're going from like theory to reality. And one of the first things you have to consider is, how do you represent a beam of particles? How do you represent them in your theory? And this goes to the heart, I think, of this of what quantum theory is about. Quantum theory is about ensembles. In other words, you take a lot of particles, not individuals. And I think some people, I'm not being patronised, I think some people sort of forget that quantum mechanics is a statistical theory. It's not it's not a theory of individuals. It's a theory of populations or ensembles, and it's a bit like when we're looking at populations of human beings and about what they do. You can't track one. Sorry, excuse me. Can't track one. You track a million, and that's what you. And quantum mechanics is very similar. Okay, what do we wanted to do to go on to is go on to looking at what we call a double Stern-Gerlach, and again, Peter, you see I've got the reference up there. And what we're talking about there is applying these ideas to a Stern-Gerlach experiment to show the evolution of flow lines. Now, the approximation, when you work out, and in fact, it was Bohm's book on quantum mechanics, which I think has the best explanation of this. When you actually use, when you first work out Stern-Gerlach, theoretically, you actually use what I call the impulse approximation. In other words, what you assume is that inside the magnet, even though it's a long magnet, can be several centimeters long, that within that, the spin axes of the particles change, abruptly, and they're all sort of randomized, and suddenly they all jump into the 3 states that we see for the helium, or 5, or whatever it is for the other particles, for the other gases. So but if you apply the quantum potential theory to it, right, and don't use the impulse approximation, when you do that, you start to see a totally different picture. That in fact, you start to see a much more slowly operating. And one of the big surprises was, and Peter actually showed this quite well, was that actually you start to see the quantum potential acting outside of the magnet, and that was and the way we wanted to try and bring that out, and Peter can give greater details. I don't know what he's talking about this week, but anyway, he might give better details on this. But if you take this diagram, which I've got up here, he used silver atoms because that's what the original Stern-Gerlach experiment used. But that doesn't matter. The two brown lines are just schematics of the two Stern-Gerlach magnets, all right? The first one where the particles enter the system, and then the second one. And what you start to see is that what you expect, or what is thought, is that when it comes out the second second Stern-Gerlach, all right, this is spin half, by the way, not spin one as the helium one was. So there's only two beams coming out of the first magnet, all right, up and down. And then when they go through the second one, the ones that are up flipped downwards, and you expect the beam to go straight down. And that's what we think we observe, because obviously all we're doing is observing at the very end. We're not observing the behavior in between. But in fact, if you believe the quantum potential ideas and things like no crossing theorems and so on that come out of it, then in fact the particles don't do that at all. They do this rather strange thing, really, if you're looking at it from just a straightforward standard quantum mechanics perspective, is that in fact the particles starting at the top, instead of going straight down, actually bend and turn up again, and also change spin. And that's indicated by the blue arrows. You can see them. And the same for the bottom. They would go up and then turn and come down. And because this turning happens outside of the magnet, as you can see there, that leads to the fact that we might be able to observe it if we could get our detector close enough to be able to view this behavior. And of course, this is a blow up of that bit in the middle. And you could imagine us placing our detector closer and closer and closer. And then you would start to see, hopefully, as you get towards the middle there, you would start to see this behavior of the things turning. So that's the idea. Right? And then Peter also produced this beautiful picture of the actual quantum potential, which is, and hopefully, Peter, you won't kick me in the head next time we see each other if I've got this wrong, but it's actually shown in, I think it's black there. And you can see the quantum potential is definitely very active outside of the magnets, which I think everyone would agree is not what we would normally expect. Certainly not standard, wouldn't be predicted by what you would call standard quantum mechanics. Okay, so that ends that. That's the program we wanted to move on to. Sadly, I've retired, so I'm hoping Vincenzo and another guy who's taken over will actually move on to that. But anyway, if not, then it leaves the field open for anybody else who wants to have a go. Now, what I wanted to do is move on and look at interference. Now, I'm not going to go through all the work that we've done. I wanted to start off, and this is kind of related to what Ismo was talking about earlier. Now, when the whole idea of when de Broglie came out with this whole idea of particle wave duality, and he gave his famous de Broglie equations, which showed us how to do this. There was this, obviously, it did throw up, as Ismo beautifully showed, that in fact it threw up this complete question about, well, is it a particle, is it a wave, and so on. And so obviously the thing to do would be to test it. Now, this wasn't the test, what I'm showing you here, but it's the one which I like. And this was done by Mullensteep and Duka in Germany, and they did it electrostatically. And this, I'm going to show you the result first, and then I'll explain briefly how they did it. And I want to then just ask at the end, I'm going to ask this question about, exactly what happens. Now, you can see what they do is I'll explain in a moment, but when they turn up the electric field, all right, on the biprism, electrostatic biprism, they actually, you can see there quite clearly as you go from top to bottom how the interference pattern slowly emerges. And I think when I first saw this, when I read this paper, and I hold my hand up that it was Google Translate, which it's in German. I couldn't find an English translation, so I spent a few train journeys, me and Google Translate, putting this together, which shows you that commuting on a train can be worthwhile after all. But anyway, so that's picture, and I think it's pretty convincing. You can see that, in fact, as you tune the biprism, then you see the diffraction pattern appearing. Now, exactly how did they do it? Well, it was based on an optical principle, and if you look at the left-hand diagram here, you can see that there's a slit at the top where the light comes in and hits the biprism, and what happens is that it sets up like it was two imaginary, or whatever the word is, virtual sources, which are shown as SI1 and SI2, and or SL, I'm not sure. Anyway, and they then come out the bottom of the biprism, and then you can tune it up, and actually you can see the interference pattern. Now, what they did was they invented an electrostatic. Well, I say they invented. All right, they used an electrostatic version of this, which is a very simple device. It's you imagine it being a bit complicated, but it isn't. Where you got on the right-hand diagram, where you've got the electrons coming at the top, they're accelerated quite fast. It's about 20 kV, 20 kilovolt acceleration voltage. Now, Simon's in the audience, so he might be able to tell me whether that's exceptional or not. It seems a lot of voltage to me, but anyway, he might have a view on that, as he deals with this stuff all the time. That's his speciality, accelerating particles. But you bring them in at the top, and then and this is a very simple device. It's simply a fiber. Where F is, it's a fiber. It was gold-covered fiber, and you put a voltage on there, and it's 7 volts, believe it or not. It's a very small voltage. And then you've got 2 other electrodes, left and right there, which are earthed. And you set up this electric field between those. And actually, they mapped out the electric field. They used something called an electrolytic trough. I don't know if you've ever heard of one, but it's a bit like when we did all the experiments as children with magnets with iron filings, and you use the iron filings to see the magnetic field. Well, this is a similar thing, so you can map out the electric field, and that's what they used to be able to map it out. There is a picture on the original paper which shows exactly how the field looks like. I was going to produce it here, but A, it's quite complicated, and B, because of the transference from the paper, it becomes a bit blurry. You can see this picture is not totally sharp, but it becomes a bit of a mess. So I didn't want to dwell on it. Now, what they also show is the original one. When you got this diffraction pattern, you see in the middle, that black bit, that is actually the shadow cast by the fiber. And so you can see that's where you got that dip in the middle. But then you start to see the diffraction pattern building up either side. Right, now if we go over to what we did, and in fact for our experiment, instead of using helium, we used argon. That was more of a practical matter rather than a physics thing. It was really just a practical. We had equipment already available, and essentially what you do is you take a real grating, drop the particles, the argon particles in there, through there, and you get your experiment, you get your pattern. And in fact, this experiment, you see it's very similar to what the previous one. It's full of vacuum chambers and what have you. Argon's coming in on the side. We have to slide it right down, which is why we have a thing called a Siemens slower in there. And in fact, if I go to this picture, at the very end of that process, you see it's lit up there. That is what we call the science chamber, and that's where the action was happening. And what happened was the particles are all brought to a standstill, and then they're dropped under gravity through the diffraction grating, and it's done. This is a magneto-optical trap, and then you can see the particles are dropped from top to bottom. And the problem is, though, of course, is that you can eventually lose any coherence you might have, and they just disperse. Sorry, excuse me.
So would it have another 5 minutes? Would it be able?
Oh, sorry, have I run over?
No, but 5 minutes.
Yeah, I've only got a couple of slides to go.
Yeah, 5 minutes.
Yeah.
5 minutes.
Oh, this is the grating. I just wanted to show you. This is the actual pattern. This is what it looks like. Right, you can see quite clearly diffraction pattern built up using the argon atoms. And this is a little video. I always love these little videos. I don't know why I get a bit excited by them. But you see atoms appearing on the screen in real time. It's obviously a bit speedy up, but you know. And then, all right, I won't go through this. You've seen these all. I presume Chris has shown these to you, so I won't go into that. And here's the picture I love because dear old Basil's still looking sprightly there, and even me in it. And Vincenzo, by the way, for those of you who don't know, is the guy in front of Basil, bottom left. He's the guy who built all this. And also the other student who's not part of our group anymore, guy in the beard who's in front of me, he built the argon experiment. So now the question I wanted to ask, and this is a question I wanted to pose, was this. The electron diffraction used electrostatic electric field, basically. Whereas we are obviously proposing that the non-electromagnetic one is using the quantum potential. So the question I wanted to ask, and this is just totally open, is could we compare and contrast these two experiments and see how the electric field, the electrostatic field, actually, how does it do it compared to how the quantum potential does it? In other words, could we learn lessons about the quantum potential from that comparison? Because they both achieve the same result. It's just that one is affecting the spin the mass or the momentum of the particle, and the other one is obviously from the charge of the particle. And so it would be an interesting comparison. I'm not sure it's ever been done, but I think it might be interesting because don't forget these diffraction type, these electrostatic lenses and all that are now used extensively in things like electron microscopes and so on. So they're well founded. Anyway, so that's it. I'm done.
Thank you.
We might have one or two very quick questions if somebody has.
Okay. Speak up though, so I can hear you.
Just for that last part.
Which bit, mate? That one?
No, your question.
Oh yeah.
You should think about your gold filament and your plates there. That's your lens. That's your Stern-Gerlach. So that's anything right, after that, if things are shielded properly, that's where the quantum potential works.
Oh, okay. So you're suggesting, because it's not Stern-Gerlach per se, is it?
No, but it's
the interaction between the wave particles, the wave nature, I think, and also the
lens. The lens.
You're saying after that.
After that, where there's no electric field, it's only the quantum potential. If we kind of treat it, that would give rise to the interference.
Yep. Okay.
Okay. Any other questions?
Robert, this is Tahir. Just my best wishes, all of our best wishes
Tahir.
for your operation.
Thank you.
Well, here. Haven't seen you for ages,
Thank you so
mate.
much.
It's great to see you. Be
Yeah,
well.
great to
Happy
see you.
operation.
How are you? All right.
Fantastic. Great to see you. It's great to see
Good,
Michael
good.
here as well. We'll keep on supporting everything you're doing.
Thank you very much.
Cheers.
I'd like to mention that Tahir was the one who financed Basil's 80th birthday bash 10 years ago. So I'd like to give him a little bit of a shout out for that. Thank you. You've got a question, Tahir?
Rob, we'll be in touch. So I'll
All right,
bye
mate.
for now.
Best wishes.
Bye-bye.
Thanks
Take
very much.
care.
Bye-bye.
Sorry I can't be there. Bye-bye.
Cheerio, Bob.